Ji Hassan, are you there?
Yes, sir.
Okay. So we will start with biological molecules today. Biological molecules can be described as substances found in living organisms or molecules found in living organisms. So biological means found or something associated with the living organisms. We have 4 examples in our syllabus. We have carbohydrates, lipids, proteins, and water in our syllabus. We will also discuss DNA and RNA. These are other biological molecules, but we'll discuss in another chapter, not here in this chapter. Okay, so let's see carbohydrates. We'll differentiate between the carbohydrates, lipids, proteins, and we will discuss their roles and structures of example molecules in carbohydrates, lipids, and proteins. Okay, so let's see carbohydrates. Carbohydrates can be described as, if you look at this word, carbohydrate, so you see it has 2 parts. The first part is carbo, that is from carbon. And the second word you see, that is hydrate. So hydrate means adding water. So if water is added into, the carbon, like carbon plus H2O, that would make CH2O. So compounds of hydrated carbon are known as carbohydrates. Okay. And in these molecules, we have hydrogen to oxygen ratio the same as that of H2O. We will compare carbohydrates with fats or lipids, and you will see lipids don't have hydrogen to oxygen ratio the same as that of NH2O. They are extremely rich in hydrogen as compared to carbohydrates. There are 3 examples or 3 classes of carbohydrates: monosaccharides, disaccharides, and polysaccharides. Monosaccharides have single sugar unit. Okay, they are sweet in taste and they are water soluble, and they are known as simple sugars. Disaccharides consist of 2 sugar units. And polysaccharides consist of many sugar units, and they are water insoluble. Polysaccharides are water insoluble, whereas monosaccharides and disaccharides are water soluble, and these are known as simple sugars. Okay, so let's see monosaccharides first. Monosaccharides consist of single sugar unit. Mono stands for single, and saccharide is for the sugar unit. So they have single sugar unit, and they are classified into various groups like trioses, tetroses, pentoses, and hexoses. They are named on the basis of number of carbon found in them. If they have 3 carbon, they are known as trioses. If they have 4 carbon, they are known as tetroses. If they have 5 carbon, they are known as pentoses. And if there's 6 carbon, they are known as hexoses. So if we write formulas for each, for 3 carbon, this will have C3, H6, and O3. Whereas for tetroses, you will have C4, H8, and O4. For pentoses, you will have C5, H10, and O5. And for hexoses, you will see they are C6, H12, and O6. This is what we'll discuss in detail. Okay, hexoses. And there are two examples of hexoses that we'll discuss. One is glucose and other is fructose. There are examples of the other monosaccharides as well, like pentoses, which is, ribose. But we'll not discuss the structure of pentoses or the ribose in detail, as it is not included in our syllabus. We have examples of trioses in our, we'll discuss in some other parts of the syllabus, but not their structures actually. The structure of glucose and fructose is only in our syllabus, and that's what we'll discuss in detail one by one. So if you look at all these formulas, for example, for trioses, it is C3, H6, and O3 for this, and for the pentoses and for hexoses, we can generalize this formula like C, H2, and O multiplied by N, where you see N is either greater than or equal to 3, or it is equal to or smaller than 7. So only these are the types of monosaccharides. There are heptoses as well that have 7 carbon. Heptoses that have 7 carbon, but we don't need to know them. And there are no examples of heptoses in our syllabus. Okay, so these are monosaccharides. And this is the general formula for monosaccharides. So let's see glucose. Glucose, as you already know, it is a hexose sugar. And it is monomer unit of many polysaccharides. Okay, we'll discuss what does it mean. And if you look at its structural formula, we can have its straight chain formula, and we can have its ring chain formula, ring structure or ring formula. So let's see, if I draw a straight chain formula, we can have 6 carbon. As this is hexose sugar, it has C6, H12, and O6 formula. Okay, this is molecular formula. And structural formula will have, 6 carbon. Carbon number 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. 6 carbon drawn in a chain, as there are 6 carbon. Carbon number 3 will have an OH group on left side, and the rest of the others will have OH group, hydroxyl group. Every carbon has a hydroxyl group attached with it. So we will draw all of them on, the right side, except carbon number 3. And as the valency of the carbon is, 4, so we will complete this valency by writing another hydrogen on the other side of it. However, carbon number 2 has double bonded oxygen with it, and a hydrogen here as well. Okay, so this carbon is known as, this carbon number 1 is known as terminal carbonyl carbon. And such carbohydrates which have terminal carbonyl carbon are known as aldoses or aldo sugar. So glucose is an aldo sugar or an aldose. Okay, so this is straight chain formula. There are two types. When we dissolve this glucose in water, it takes ring shape, and there are two types of glucose types. One is an alpha glucose and the other is beta glucose. Let's see the structure of alpha glucose and beta glucose one by one. In ring structure, if we look at this, the straight chain formula, this carbon number 1, how the ring is formed in between, the different carbon number 1 and carbon number 5, that actually makes a ring here. Okay, and this ring is formed due to this by this oxygen in between. Why this oxygen in between? Like oxygen makes double bonding, and one bond is made with this carbon number 1 and other is made with this carbon number 5, and so this bends this chain upon itself, and as a consequence this would make a hexagonal structure. And the hexagonal structure can be drawn showing this is an oxygen here. On one side it has carbon number 1, this is carbon number 1, and on other side it has carbon number 5. The other carbons from carbon number 1 to carbon number 5 include carbon number 2, then carbon number 3 and carbon number 4. So this is a hexagonal ring. Do you see there are 5 carbon which make a part of a ring? The 6th carbon, as glucose has 6 carbon, so 6 carbon is out of the ring. Okay, and as every carbon has a hydroxyl group and a hydrogen attached with it, so we should draw the positions of hydroxyl groups and hydrogen with each of these carbon. In alpha glucose, on carbon number 1, OH group is below the plane of the ring, and H is above the plane of the ring. Okay, on carbon number 2, it has an OH group here, it is an H here, and on carbon number 3, position of an OH and H is indifferent than carbon number 2. Okay, and carbon number 4 has an OH group here and hydrogen here. Carbon number 5 has hydrogen with it, and carbon number 6 has an OH group and 2 hydrogen to complete 4 valency of this carbon number 6. So this is an alpha glucose. Okay, we can represent this structure without these carbons in it, and that's known as a skeletal formula. So in a skeletal formula, you can simply draw showing no carbon and no hydroxyl groups with it, except on carbon number 1. You can show on the other carbons as well, OH groups and hydrogen. These are the different ways you can represent this, the alpha glucose ring structure. In alpha glucose and beta glucose, there is a difference in the position of this OH group on carbon number 1 only. Okay, so both of them, they differ from each other on carbon number 1. They have a different position of an OH group. In beta glucose, if I redraw beta glucose, so let's see. Similarly, this has a hexagonal ring. Okay, here it has an oxygen. This is the hexagonal ring. At rest of the other positions, alpha glucose and beta glucose are the same. So if I draw an OH group here and hydrogen here, you see this will be an alpha glucose. Okay, but how it would differ in case of beta glucose, if I draw that, this is an O, this is C, and this is C. So this is hexagonal ring again. The rest of the other carbons have the same arrangement of hydroxyl groups and hydrogen on them, but carbon number 1 has now an OH group here above the plane, and an H is here below the plane of the ring. So this is a beta glucose. So do you see this is a difference in between these two at position number carbon number 1 of both these alpha and beta glucose. At rest of the other positions, the hydroxyl groups are the same. For example, at carbon number 2, there is OH group here in both. At carbon number 3, an OH group is here. And on carbon number 4, this is an OH group here, an H here, an H here. And you will have carbon number 6 here, carbon number 6 here. And this has an OH group here, hydrogen. Okay. Now, let's see disaccharides. Di means 2 and saccharides mean sugar units. So disaccharides have 2 sugar units joined together by condensation. And the bonding in between them is known as by glycosidic linkages. We look at how the glycosidic linkages are formed and how condensation takes place. Condensation, I am sure you already know. Condensation means joining of 2 molecules by elimination of H2O molecule. Okay, so we have a structure of sucrose. Sucrose is an example of disaccharide. But we will also look at the structure of maltose and formation of maltose and formation of sucrose. So let's see formation of maltose first or formation of a disaccharide first. Maltose, as I said, is a disaccharide, and it is made from 2 alpha glucose units. To make a structure of maltose, we should draw 2 alpha glucose. Okay, so this is an OH group here, an H here, an OH here, an H here, H, and an OH here, H, H and CH2 OH. We can write this carbon 6 as well. And if I draw another alpha glucose, that would be, C, this is carbon number 4, carbon, and then O, this is carbon number 1 here, we will have, okay. Similarly, this will have an OH. If I number these carbon here, on the first molecule, this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, this is carbon number 5, and this is carbon number 6. Similarly, this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, this is carbon number 5, and this is carbon number 6. So carbon number 1 has an OH group here, and similarly carbon number 1 has an OH group here too. And the rest of the other carbon have, same positions of hydroxyl groups and hydrogen. So these are alpha glucose units. These are 2 alpha glucose units. An enzyme brings these 2 hydroxyl groups in an active site and removes hydroxyl group from one and hydrogen from the other. It doesn't matter from which of the carbon you are removing the hydroxyl group and from where you are moving the hydrogen, but it should be the hydroxyl group from one carbon and hydrogen from the hydroxyl group of another carbon. Okay, so this would be eliminated as water. Okay, one water molecule is eliminated. This OH from here, from carbon number 4, and this hydrogen from carbon number 1 are removed and joined with a water molecule. And the remaining molecule will make a bond between carbon number 1 from this molecule through an oxygen here. And this is carbon number 4 here. This is known as glycosidic linkage. Glycosidic linkage. As you can see, this linkage is in between carbon number 1 and carbon number 4 of the 2 alpha glucose. So you can say it is alpha 1,4 glycosidic linkage. Okay. The rest of the molecule can be, drawn similarly. So this is how a disaccharide is made. This process of joining these two, which has been shown by this arrow, is known as condensation. Okay, so this is condensation. The opposite of it is known as hydrolysis. So disaccharides can also be defined as which can be hydrolyzed into 2 monomer units. So this is structure of maltose, which is a disaccharide, and when it is broken down by hydrolysis, you see 2 alpha glucose are made in this case, right? So this is how disaccharides are made. Now, to look at the formation of sucrose, let's have a look at, so let's see. Just a minute. Okay, so let's see. Structure of fructose first, and then we will look at the formation of a sucrose. Sucrose, you know, is a disaccharide uh, which is made from sucrose is a disaccharide which upon hydrolysis, if it is broken down, that would break down into uh, an alpha glucose and a fructose molecule. And these two molecules are joined up by condensation to make sucrose and water molecule again. So this arrow uh, in this right hand direction that shows condensation. This is condensation. Okay, so this is condensation, whereas this in the other direction is hydrolysis. So let's see the structure of fructose. Fructose, as I said, uh, is a hexose sugar too, but it has a different structure than the other hexose, which is an alpha glucose. Alpha glucose, you already know, it is a hexagonal sugar. So it has a hexagonal structure. It has 6 carbon, carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Okay, and this has an OH group here, hydrogen here, 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 and CH2OH here. So this is an alpha glucose. Okay, but fructose has a pentagonal structure. Pentagonal structure means the ring has 5 corners or 5 sides. So this is C here, this is C here, and this is carbon and carbon here. This is pentagonal structure. In fructose molecule, there are 4 carbon in the ring, whereas in glucose, there are 5 carbons in the ring. Okay. 2 carbon are out of the ring in this case. This is carbon number 1. This is carbon number 2. This is carbon number 3. This is carbon number 4. This is carbon number 5. And you have this carbon number 6 here. Okay. Carbon number 1 has similarly, you can write CH2OH here. Carbon number 2 has an OH group here. Carbon number 3 has an OH group here and hydrogen here outside. This has an OH group here, hydrogen here. Carbon number 5 has an H here, and carbon number 6 has CH2OH here. Okay. Now the bonding in between these two takes place between carbon number 1 of alpha glucose and carbon number 2 of fructose. And to do so, you should bring these OH groups in the same, this OH group and this OH group in the same plane. Okay, now in this case, you see they are not in the same plane. And to do so, we will have to rotate it so that we could bring them in, I guess, this way. So let us see if I can. No, let me do that again. Yes. So now this is, now these two OH groups are in the same plane. Here you see I have this flipped this, fructose. This is structure of fructose, and that has been flipped so that an OH group on this carbon, an OH on this carbon number 2, that lie in the same plane. And then similarly, an OH group from the one and hydrogen from the other will be eliminated. That would be removed as a water. One water molecule will be eliminated, and these two will be joined together. So to join them together, let me, copy it, and we can see. Let me just copy it, and we can paste it here. Okay. So I have pasted it again here. So do you see this OH group from here will be removed, and this hydrogen will be removed from here, and a bond will be formed in between this carbon number 1 and this carbon number 2 through an oxygen in between them. So this bond formed in between carbon 1 and carbon 2 is known as a glycosidic linkage, and this is the structure of a sucrose molecule. Okay, so that's about disaccharides. In our next lesson, we'll discuss the polysaccharides. And in polysaccharides, we have storage polysaccharide and structural polysaccharides. In storage polysaccharides, we will discuss structure of starch, in which amylose and amylopectin structure will be discussed, and then glycogen. And then in the structural polysaccharides, we'll discuss the structure of cellulose. And in the next class, we'll be able to finish these carbohydrates. So that's it for now.
Allah Hafiz, sir.
Allah Hafiz.